Black holes have long captured the human imagination as dark, insatiable monsters lurking in the cosmos, devouring anything that happens to drift too close. Popular explanations often describe them as ominous voids in the fabric of spacetime, regions so dense and so powerful that not even light can resist their pull. In this simplified picture, a black hole sits silently in space, pulling matter inward with relentless hunger, stretching anything that nears it into long, thin strands of cosmic spaghetti before swallowing it forever. But as striking as that image may be, the true nature of black holes is far more complex, far more mysterious, and far more fascinating than the traditional description suggests. In recent years, especially with the groundbreaking discoveries made in 2019, scientists have uncovered insights that challenge old assumptions and open entirely new avenues of thought about these extreme objects. Far from being mere cosmic vacuum cleaners, black holes are dynamic, information-rich, and perhaps even portals into deeper mysteries of the universe. One of the most spectacular breakthroughs came when physicists finally achieved what once seemed impossible: capturing an image of a black hole. For decades, black holes were considered unobservable directly because their defining feature, their event horizon, allows no light to escape. However, in 2019, the Event Horizon Telescope (EHT), a global network of radio observatories, succeeded in imaging the supermassive black hole at the center of the galaxy M87, located about 53 million light-years from Earth. The result was a glowing, donut-shaped ring surrounding a shadowy core, a landmark achievement that offered humanity its first direct look at one of nature's strangest phenomena. Although the image appeared grainy and faint, the object it portrayed was anything but small, a monstrous black hole over 5 billion times the mass of the Sun, with an event horizon so large it could engulf our entire solar system. The bright ring captured in the EHT image was not the black hole itself, but rather its accretion disk, the swirling, superheated matter that orbits the event horizon before plunging into the abyss. As this matter spirals inward at tremendous speeds, it heats up due to friction and interaction with magnetic fields, producing light across the electromagnetic spectrum, including the radio waves used to produce the famous image. The orange glow is essentially the last cry of matter about to disappear forever behind the veil of the event horizon. This visualization confirmed long-standing predictions based on Einstein's general theory of relativity and gave scientists a new tool for studying black holes not as theoretical constructs, but as observable astrophysical objects. Beyond the excitement of imaging a black hole, 2019 also brought renewed attention to a long-standing debate about whether black holes have hair. For decades, physicists adhered to the so-called no-hair theorem, which proposed that black holes are remarkably simple objects. According to this theorem, once a black hole forms and stabilizes, all the details about the matter that formed it, its composition, distribution, temperature, magnetic fields, and every other characteristic, vanish from the universe. Only three basic properties remain: mass, electric charge, and angular momentum. In this view, a black hole is completely featureless and unchanging, something like a cosmic cue ball. Two black holes with the same mass, charge, and spin would be entirely indistinguishable, no matter how differently they formed or what they consumed. This idea troubled many physicists, including Stephen Hawking, because it implied that information might be destroyed when it falls into a black hole, which contradicts the fundamental principles of quantum mechanics. In 2016, Hawking and several collaborators proposed that black holes might not be completely bald after all. They suggested that subtle features, distortions or fluctuations around the event horizon, could encode information about the matter that fell in. These hypothetical features were whimsically labeled hair. If true, the presence of hair could solve or at least soften the black hole information paradox, the long-standing mystery of whether information truly disappears inside a black hole or is somehow preserved. Research continued, and by 2018, a study claimed that extreme black holes, objects with the maximum possible electric charge, making them highly unusual in nature, might possess distinguishable hair-like features. This was intriguing but limited. because real astrophysical black holes are unlikely to hold much charge. Then, in 2019, scientists expanded the idea further. New work suggested that even more typical black holes, those that spin near their theoretical limits but remain uncharged, or those that possess maximum charge but do not rotate, might also grow forms of hair. These features arise from the mathematical structure of the horizons themselves, specifically the event horizon and an inner region called the Cauchy horizon, where cause and effect begin to behave in strange ways. The research suggested that black holes could temporarily form unique, identifiable patterns that encode information about their past interactions. However, these hairs are not permanent. Just as quickly as they appear, they decay, smoothing out until the black hole becomes effectively bald again. This transient quality makes them incredibly difficult to observe directly. The hairs are like ripples on the surface of a pond that fade soon after a stone is thrown in. While the existence of these ripples indicates something happened, the details vanish almost immediately. In physical terms, the information may be preserved in some subtle form, but detecting it presents enormous challenges. The idea that black holes might briefly sprout hair before settling back into smooth simplicity has profound implications for our understanding of physics. It suggests that black holes could store and release information in subtle ways instead of destroying it outright. This research also opens the possibility that gravitational wave detectors, such as LIGO, Virgo, and the upcoming Einstein telescope, may one day detect these signatures. When two black holes merge, they produce gravitational waves that ripple through the universe. After the collision, the newly formed black hole rings like a bell, emitting patterns of gravitational waves that depend on its internal characteristics. If black holes truly have hair, even briefly, these ring-down patterns may carry the fingerprints of that hair, providing evidence about the black hole's history. The potential to use gravitational waves as tools for probing the structure of black holes represents one of the most exciting developments in modern astrophysics. Before 2015, gravitational waves were purely theoretical, predicted by Einstein but never detected. The first detection changed that, revealing a universe alive with collisions of massive objects. As detectors improve in sensitivity, scientists expect to gather more detailed data about the dynamics of black hole mergers. This could finally allow researchers to test theories about hair and potentially even discover new physics that extends beyond Einstein's relativity. Alongside these theoretical developments, the study of black holes also raises deeper questions about their interiors, regions we cannot observe but can theorize about. Some physicists wonder whether black holes might be gateways to other regions of spacetime, such as wormholes or baby universes. While such ideas are speculative, they arise naturally from certain mathematical extensions of general relativity and quantum gravity. If information entering a black hole somehow continues to exist, perhaps it is stored in a way that connects to something beyond our universe, or perhaps the interior structure is much richer than the simple singularity once assumed. Although much remains unknown, each new discovery about black holes reveals not only their complexity, but also the astonishing interconnectedness of cosmic physics. What began as a simple description of black holes as dense, dark singularities has expanded into a vibrant field at the crossroads of relativity, quantum mechanics, thermodynamics, and observational astronomy. Black holes challenge our understanding of space, time, information, energy, and even the ultimate structure of reality. They are not merely destructive forces, but also laboratories for studying nature at its most extreme. The breakthroughs of 2019 marked a turning point. They showed that black holes can be imaged, studied, and understood in ways once thought impossible. They suggested that black holes might possess fleeting structures that preserve information. They demonstrated the power of global cooperation in science, with observatories around the world working together as one vast instrument. And they reminded us that even the darkest, most enigmatic objects in the universe can be illuminated with patience, creativity, and ingenuity. As technology advances, scientists expect to capture even sharper images of black holes, observe their changes over time, and detect more detailed gravitational wave signatures from their mergers. With each improvement, we move closer to unraveling mysteries that once seemed beyond human reach. Black holes may forever remain strange and otherworldly, but thanks to the discoveries of the past decade, they are no longer invisible, unknowable monsters. They are windows into the deepest truths of the cosmos, truths that continue to challenge, inspire, and expand our understanding of the universe itself.